Hi and welcome! Welcome to the second part about OpenGL. In the next series of lectures, we're going to learn about matrix transformations, OpenGL coordinates, and cameras in OpenGL. But let's start with the lecture. In this lecture, I'm going to focus on some basic concepts of computer graphics we need to know in order to use OpenGL. In this lecture, I want to make three key points. First, the best way to transform graphics objects with rotation, translation, and scaling operation is to multiply each vertex of the graphics object by a transformation matrix. Second, we have transformation matrices for scaling, translation, and rotation operations. Third, the combination of two or more transformations is represented by the matrix-matrix multiplication of the matrices. At this point, we now know how to create objects, color them, but they are still not that interesting since they are all static objects. We could make them move by changing their vertices and reconfigure their vertex buffers each frame. But this is cumbersome and costs quite some processing power. There are much better ways to transform an object, and that is by using multiple matrix objects. Matrices are very powerful mathematical constructs, and we are going to look at them and their equivalent transformation in this lecture. But why do we care about matrix vector multiplication? Well, it just so happens that there are lots of interesting 2D and 3D transformation we can place inside the matrix. Multiplying that matrix with our vector basically transforms our vector. In OpenGL, we use 4x4 matrices to express a whole bunch of transformations like translation, rotation, and stretching of an object. The single vertex coordinate is represented with a four-dimensional vector with x, y, and z coordinates, and 1 as last coordinate. To transform one vector, we multiply this transformation matrix by the vector to obtain a new transformed vector. In OpenGL, we usually work with the 4x4 transformation matrices for several reasons, and one of them is that most of the vectors are of size 4. The simplest transformation matrix that we can think of is the identity matrix. The identity matrix is an n by n matrix with only 0 except on its diagonal. This transformation matrix leaves a vector completely unchanged. This becomes obvious from the rules of a matrix vector multiplication. The first result element is each individual element of the first row of the matrix multiplied with each element of the vector. Since each of the row's elements are 0, except for the first one, we get 1 multiplied by 1 plus 0 multiplied by 2 plus 0 multiplied by 3 plus 0 multiplied by 4, that is equal to 1. And the same applies to the other three elements of the vector. When we are scaling a vector, we are increasing the length of the arrow by the amount we would like to scale, keeping its direction the same. Since we are working in either 2 or 3 dimensions, we can define scaling by a vector of 2 or 3 scaling variables. Let's start building a transformation matrix that does the scaling for us. We saw from the identity matrix that each of the diagonal elements were multiplied with its corresponding vector element. What if we were to change the ones in the identity matrix to 3s? In that case, we would be multiplying each of the vector elements by a value of 3, and thus effectively scale the vector by 3. If we represent the scaling variable as S1, S2, and S3, we can define a scaling matrix on any vector x, y, and z, as on these slides. Note that the third scaling vector stays 1, since it is undefined to scale the W component in a 3D space. The W component is used for other purposes, as we will see in the next slide. Translation is the process of adding another vector on the top of the original vector to return a new vector with a different position. This results in moving the vector based on a translation vector. Just like the scaling matrix, there are several locations on a 4x4 matrix that we can use to perform certain operation. For translation, those are the top 3 values of the third column. If we represent the scaling vector as tx, ty, and tz, we can define the translation matrix as in this slide. This works because all the translation values are multiplied by the vector's w column. This wouldn't have been possible with the 3x3 matrix. The W component of a vector is also known as homogeneous coordinate. To get the 3D vector from a homogeneous vector, we divide the x, y, and z coordinates by its W coordinate. We usually do not notice this since the W component is 1 most of the time. Using homogeneous coordinates has several advantages. It allows us to do translation on 3D vectors. In fact, without a W component, we can translate vectors. And also in the next lecture, we will see that the W value is used to create 3D visuals, like the perspective projection. The last basic transformation we are looking at is rotation. Rotation in 3D are specified with an angle and a rotation axis. Specified angle will rotate the object along the rotation axis that is given. When rotating 2D vectors in a 3D world, for example, we set the rotation axis to be the z-axis. Using trigonometry, it is possible to transform vectors to new rotated vectors, given an angle. This is usually done via a smart combination of sine and cosine. A rotation matrix is defined for each unit axis, where 3D space, where the angle is represented as the theta. Using the rotation matrices, we can transform our position vectors around one of the 3 unit axes, like shown on this slide. This slide shows how to calculate matrix multiplication of two 4x4 matrices. As you can see, matrix multiplication is a quite cumbersome process and very prone to errors. This gets problematic really quickly when the matrices become larger. That is also why we use computers to calculate them. The true power from using matrices for transformation is that we can combine multiple transformations in a single matrix thanks to the matrix multiplication. When multiplying matrices, the rightmost matrix is first multiplied with a vector. So you should read the multiplication from the right to the left. In general, it is advised to do first the scaling operation, then rotation, and lastly translation. Otherwise, we might get negative effect. For example, if you would do first the translation and then a scale, then the translation vector will also scale. Let's see if we can generate transformation matrix that combines several transformations. Say we have a vector x, y, and z and we want to scale it by 2 and then translate it by 1, 2, and 3 vector. We need a translation and a scaling matrix for our required steps, like in this slide. Then the resulting transformation look like the obtained result of a matrix multiplication on this slide. Running the final transformation matrix on our vector results in the following vector. Great! This is the vector that we first scaled by 2 and then translated by a vector of 1, 2, and 3. So we reach the end of this lecture. In summary, I've stressed 3 main points. First, we transform graphics objects by multiplying each vertex of the graphics object by a transformation matrix. Second, we have transformation matrices for scaling, translation, and rotation. Third, the combination of 2 or more transformations is represented by the matrix multiplication of the matrices. In the next lecture, we are going to look at how to do in practice all these transformations using a library called GLM. Talk to you soon!